Good day to everyone. Thank you very much for joining our seminar. So as usual, I will start from a very briefly remind you our rules that we try to follow. So you're very welcome to ask your questions both during the seminar and after it. During the seminar, we kindly ask you to keep your microphones and videos off. And you will be able to switch on your microphone. And there are two ways to ask questions. You can either raise your hand and we will interrupt the speaker at some point. And another way is you may want to type the question to the chat. So our today's speaker, it's my great pleasure to introduce our today's speaker, Ilya Vatnik from Novosibirsk State University, Russia. And he will give a talk about controlling and utilizing optical whispering gallery modes on the surface of optical fibers. Ilya, please.
Thank you, Anton, for presenting me. Thank you for inviting me also to this seminar. And of course, thank you, everyone, dear colleagues, for coming this day or evening to listen to me. I'm presenting here a work we've been doing in Novosibirsk State University. I'm part of some not very big but not very small scientific group from Novosibirsk. We have started this work just a few years ago, and we do appreciate the help and collaboration from group of Misha Sumetsky, who works at the similar field in Aston University in Birmingham, UK. So first, I'll just start with definitions and typical parameters of the microresonators that support whispering gallery modes. Then I'll introduce the whispering gallery modes propagating on optical fibers. I'll talk about theoretical considerations and theoretical model that explains the propagation of these modes. Then I'll show some of our recent results on the techniques, how to build, how to design, and how to shape such microresonators based on optical fibers, and how to control the propagation of whispering gallery modes. And finally, I'll briefly demonstrate some promising applications of such microresonators. Well, so to start with, I'll just want to remind some basic physics. We study optical whispering gallery modes that are resonant standing waves which can be excited in axisymmetrical systems due to effect of the total internal reflection. And in the simplest model, there is an equation which must be satisfied in order to make constructive self-interference of a mode which circulates next to the boundary, next to the surface of some optical material, axisymmetrical optical object. What's important that is there is a radius of the sphere, for instance, and n is a refractive index, and the product of r multiplied by n is an effective radius, and this amount, product of r and n, is very important, and I'll be talking about this product many times in following. Again, some simplest basic physics. There is a quantum numbers. M is a azimuthal number, which defines how many maxima we have in the maximum of intensity of a mode. We have the cross section. There are also another quantum numbers such as angular, radial, and for example, on a sphere. Oh, okay. Anyway, these three numbers fully describe the spatial distribution of a mode on some surface. There are different possible geometries of the microresonators, not only spheres, but also disk, very popular ring cavities. These 3 or 4 probably are the simplest geometries and have thus seen the most of attention over the years. There are also another kinds of geometries such as tubular, microbubbles, capillary microresonators, and so on. The key advantages of whole range of microresonators are at first small size, so small optical mode volume. Typically, it's something about hundreds of cubic microns. Because of small size, the quality factors can be extremely high. Actually, the highest quality factor was shown to be 10 to the 11 for some crystalline microresonators. These microresonators can be easily tuned, they have simple design, and they are also robust, depending on which particular way you use to excite these microresonators. Two most popular ways to couple light into microresonators using a prism or a biconical tapered fiber taper. And for example, microresonators coupled with a prism turned out to be robust enough to be launched into space. There is some kind of famous LISA mission, LISA Space Gravitational Telescope, and there will be a microresonator-based laser which will be launched to this telescope in a few years, I guess. So this microresonators kind of very robust. Actually, in our experiment we use tapers rather than prisms, but for our tasks it's not important. Well, and because of all these advantages, there are a lot of applications such as add-drop optical filters, bias sensing, laser spectrum stabilization, some nonlinear devices such as microcombs or optoelectronic oscillators, and so on and so on. Today, I'm going to focus on a particular type of geometries of microresonators, on cylindrical microresonators made of standard conventional optical fibers. It was shown some years ago, I think in early 2000s, that if we take a standard optical fiber, remove the secondary plastic coating, and launch light into the silica cladding. There can be we can excite long-living whispering gallery modes, which propagate, circulate around the surface next to the outer boundary of the cladding of the fiber. And the quality factor of such modes turned out to be quite high, 10 to the 6, without any special treatment of the fiber. So the roughness, the quality of the fiber cladding appeared to be quite good to support long-living whispering gallery modes. And it's quite good because optical fiber, every optical lab has an optical fibers, and it's probably the cheapest and the easiest way to make an optical microresonator. Actually, it was shown theoretically that quality factor of such microresonators can be as high as 10 to the 8. This is like a theoretical limit, theoretical maximum of the quality factor. If a fiber is perfectly uniform, if the cladding radius is the same at every point along the axis of the fiber, then for given azimuthal number and radial quantum number, a single high quality resonance should exist, which with spectral position with the resonance wavelength determined by the radius of the cladding, again by this simple formula. Interestingly, the mode doesn't diffract infinitely to this direction and to this direction. It keeps bounded. It keeps it exists in a confined area around the excitation point because of the multiple self-interference of the beam, which is rotating here. Again, the spectral position of the resonance mode can be measured by measuring the transmission spectrum of the coupling objects, such as microfiber, such as taper, for example. And when we look at the transmission spectrum, we will see a dip in the spectrum with the frequency, with the wavelength corresponding to a particular resonance whispering gallery mode. Well, so in the real life, fibers are not perfectly uniform, and we can easily check how uniform is the standard fiber, and that's what many people did actually. So we can just check the resonance spectrum, just check the spectrum of the modes in different places along the fiber axis, and plot a spectrogram such as presented here. On x-axis, it's a position where the mode is excited, position along the fiber. On the y-axis is the wavelength, and here we can see the dips in transmission spectrum, which changes. So the effective radius of the cladding actually changes along the fiber, and the change of the refractive of the effective radius is rather small, I should say. It's around of, if we calculate the variation of effective radius by this simple formula, it turned out to be like some nanometers per millimeters of the fiber length. So fibers turned out to be quite uniform in terms of the cladding radius.
Yeah, excuse me, may I ask you regarding the fiber? So as far as I understood in the very beginning, you noted that you are talking about the single mode telecom fibers. So the radius has to be quite small for those fibers and those modes. What is the M parameter for your mode you're discussing right now? How many? So what is a azimuthal number?
Yeah, thank you. Sorry, I just missed it. The fiber cladding has a diameter of 125 microns. It's like standard for actually for single mode fibers, for standard multi-mode telecom fibers, doesn't matter. And thus the azimuthal number should be like 300-400 for such a diameters. Okay, so the radius is 125 microns, but it varies very slightly along the fiber axis, and variations as small as a few nanometers actually. Okay, so the radius, effective radius, varies along the fiber, and it's important because the variations of effective radius is the variable that controls the propagation of whispering gallery modes in axial direction along the fiber surface. Actually, it was demonstrated by Sumetsky and also, I think, by Gorodetsky also, that axial propagation of whispering gallery modes on the surface of a cylinder can be described by one-dimensional Schrödinger equation with a potential which is linearly proportional to the effective radius variation, but not to absolute effective radius variation, but to the arbitrary effective radius variations. So actually we can obtain any phenomena which are known from one-dimensional quantum mechanics in the cylindrical microresonators, because if we can introduce different effective radius variations. Here, for example, it's a picture which I took from this paper of Sumetsky. He introduced a single potential well. Actually, just he enlarged a fiber at some point. This radius variation plays role of a potential, and if we check the resonant whispering gallery modes with different axial numbers in this potential way, well, we see the well-known case of different aging modes and different aging values and energies and a single potential well in quantum mechanics. So the idea of the cylindrical microresonators based on optical fibers, or how Sumetsky named it, SNAP, surface nanoscale axial photonics, the idea is to introduce different potentials for axial propagation for whispering gathering modes by introducing variations of effective radius. And as I will show further, this possibility sufficiently enlarges and broaden the area of possible applications for cylindrical microresonators. Before I go to applications, I'd like to discuss how to introduce the effective radius variations. Probably I skip this, it's not important, and come to kind of conventional, okay, we can talk about these methods as conventional methods to introduce effective radius variations. There are two methods. The first method comprises local annealing of the fiber surface with a focused CO2 laser radiation. So we just hit a fiber locally and it causes thermal relaxation of the tensions which were frozen in the fiber during the drawing process. So the fiber slightly increases its radius, and this results in increasing of effective radius variation, in local increasing of local radius variations. The problem with this method is that there is some distinct amount of stresses which are frozen in the fiber. So you cannot, when you release all the stresses inside, you cannot bring any more relaxation, expansion, and you cannot bring any more effective radius variations. So there is an upper limit of effective radius variations which can be brought by this writing with CO2 laser. Another type of shaping cylindrical fiber-based microresonators is to use femtosecond laser inscription, and in this case we introduce new stresses, and rather than make the existent stresses to be relaxed. And with femtosecond laser, we can introduce much more effective radius variations. In our lab, we just repeated this technique, which was proposed by Sumetsky's group. And what we found, we were surprised actually that with this method, we can bring not only positive variations of the effective radius, but also negative. It's interesting, it looks like you hit a fiber and it locally shrinks. Here is an example. We took some fiber with the, this is the spectrogram for a pristine fiber. It did have some variations, but when we heated it locally in 5 different places, we found negative variations of the effective radius, and the answer that describes this effect is that, of course, geometrical sizes of the fiber, its geometrical radius doesn't change, or at least we believe it doesn't change, but the refractive index slightly decreases, so effective radius decreases. this method of negative variations rather than positive variations can be useful in shaping the cylindrical microresonators, because negative variations are introduced at much lower temperatures. So in general, these variations can be much more local. Okay, there are other different interesting ways to introduce effective radius variations and control the propagation of whispering gallery modes. And one of them is bending of the fiber. Indeed, if one bends a fiber, he introduces stresses within the fiber material, and these stresses have a twofold effect. At first, there is a Poisson effect, so there should be expansion or construction of the fiber, so it should be a geometrical variations of the radius along the fiber axis. And the second effect is the photoelastic effect. So refractive index should also change. It's kind of tricky, difficult, sophisticated problem to predict theoretically what will be with effective radius while bending, and it turned out to be easy just to check it experimentally, and that's what we did. We just take a piece of fiber, made a loop of it, and measured the spectra of whispering gallery modes at different points along the loop, and we saw that there is indeed a variation of the effective radius that at first linearly scales with the curvature. So the larger the curvature, the larger the introduced effective radius variation. And of course, it's the largest and the top of the loop. And here and here, here and here, we saw the undisturbed effective radius. And
yeah, excuse me.
Yes. Sure.
May I ask you a question? So, in order to estimate the changes in your optical path length difference after bending or whatever, you probably have to know the azimuthal quantum number first and the axial momentum of your mode. So it may be just spinning around some point, and it may be, as far as I can imagine, maybe shifting along the fiber. So in order to estimate the real change in the radius or any geometrical parameters, you have to know the rest. So how do you know it?
You're right. If we need to know, you're absolutely right. If we need to know the exact effective radius at a point, we actually should know the axial and azimuthal number and all numbers. But if we look at the mode with the smallest axial number, so we just assume that there is that the axial part of a wave vector is negligibly small. So if we look, for example, at this point, spectrum consists of a lot different modes with a lot of different axial numbers. But if we look at this very point, at the mode with the lowest axial number, we can, for rough estimations, we can still use this simple formula. Actually, you see, you don't need to know azimuthal number in order to derive the variation of effective radius. That's my first point. And the second point, if you need just an estimation, you don't you don't worry about any quantum mechanics. You don't worry about any axial numbers. You just take the you just take the smallest mode with the negligible axial wave vector and use this formula for estimations.
Okay. Thank you.
Okay, it's probably not clear, but
no, it's clear. So your radius already contains the information about your azimuthal number with account for the wavelength. So it is somehow cancelled from. So this formula already accounts for
exactly. It already contains the m, and you actually derive only the variation.
Okay, I see. Thank you very much. Thank you.
The question is rather difficult actually, because if you want to get the precise amount of the variation, you should solve the inverse scattering problem just for one-dimensional quantum mechanics. Sorry, just to derive the exact function of the potential, and this is what we don't do. So we just make an estimation using the simple formula. Okay, so if we take a look closer to the top of the loop, we can see there are a lot of modes with different axial numbers. So we do make an axial resonator for these axial modes. So we do introduce a potential well in which a lot of modes oscillate. What's interesting with the bending, that it's an easily tunable way to introduce effective radius variations. In order to demonstrate it, we performed such an experiment. We put ends of a fiber piece through a narrow plastic tube. And this simple setup allowed us to fix the loop shape at first, and at second we can change its size by easily pushing or pulling fiber ends here. So we check effective radius variations for different loop sizes and obtained this empiric formula that describes again that effective radius variations are linearly depends on the curvature or inverse curvature radius, but it also scales with the radius of the fiber and inverse radius of the loop. So this way bending is might be very useful for tuning the cylindrical microresonators. Well, there are another possibilities to use geometrical features of the fiber in order to control whispering gallery mode propagation, and other of them is the use of the fiber cleave, fiber end. Indeed, if we look to the whispering gallery mode in ray approximation, the mode represents a spiral with a small pitch because axial propagation constant is typically 100 times smaller than the full net wave vector. So the spiral axis, the pitch actually is very small, not as it's drawn here. And this spiral, the incident angle for this spiral at the perpendicular surface of the fiber end can be quite large. So in general, we may expect total internal reflection also at the fiber end. I'll just skip this and demonstrate the experiment which experiment which demonstrated the reflection of whispering gallery modes from the fiber end. In this experiment, we launch optical pulses into the whispering gallery modes rather than a continuous wave radiation. So we use two tapers, one taper to launch the pulse, which started to circulate and probably reflect from the end and going back. And we used another taper to probe the intensity of a pulse in different points along the surface, along the fiber. And this is what we saw. So actually different whispering gallery modes with different azimuthal numbers were excited. Some of them propagated too fast, so it appeared, for us, it appeared everywhere in the resonator, but for slower modes, we saw the good picture of the pulse which propagated to the fiber cleave, reflected from the fiber end and propagated in backward direction. We checked it for different detunings for pulses with different group velocities. We calculated the reflection coefficient for the fiber cleave and found it to be quite high. It reached 70%, and I believe it can be 100%. So, because I think in our case, the fiber cleave was not perfect. So we believe that there is a total internal reflection at the fiber end. And this feature can be also used to build up an axial resonators for axial propagation of whispering gallery modes. Now I come to some applications. First of all, because of propagation speed in the axial direction for whispering gallery modes is like 1,000 times smaller than that of than the velocity of light in vacuum. The cylindrical microresonators may be a good choice for optical delay lines. Moreover, the dispersion of the whispering gallery modes of axial propagating whispering gallery modes is determined by the potential, or in our case, by the effective radius variation. So if one can build a proper shaped effective radius profile, he potentially can build a dispersionless potential. Actually, from one-dimensional quantum mechanics, one-dimensional quantum mechanics says that potential should be parabolic in order to get dispersionless propagation. This is exactly what Professor Sumetsky did in 2013. He made a cylindrical microresonator made of optical fiber with a semi-parabolic shape of effective radius variation, and he demonstrated that the pulse launched into the resonator propagated inside without dispersion and went out after some 2.7 nanosecond. So this type of microresonators can be used as a small, kind of robust delay line. And when we're talking about tuning, the tuning is interesting here because the advantage is that the delay time can be adjusted by changing the loop size. Because when we change the loop size, we change the profile of the effective radius radiation. Disadvantage is that the potential introduced by bending has parabolic form only at some small area next to the top of the loop. So somewhere here or here on the spectrogram, the shape is not parabolic anymore. Just to prove an idea of banded delay line, we performed kind of first experiments. We launched a pulse into one taper, which was placed in some place at the loop, and collected the pulse through the second taper, which was placed here, and we just show that pulse indeed acquired some considerable delay. In our case, it was around 2 nanoseconds. But in these experiments, the dispersion was quite high, and also the coupling losses were high. So we should go further with these experiments. Again, bending delay lines can be very useful because you can adjust in some range, you can adjust the delay time. Okay, finally, I just show some, actually 2 promising applications which were proposed also by Professor Sumetsky. They still didn't appear in experiments, so it's still an interesting topic. The first one is at biosensing using a cylindrical microresonator. Idea is to introduce a triangle potential or triangle effective radius variation profile on the surface of microresonator. And if we measure the spectrum at this point, at the very top of the triangle, we will see the number of resonances which correspond to the whole set of modes. Some of them living just next to the top, some of them living everywhere. Well, if some small particle, biological cell, some kind of small object appears at the surface somewhere, it of course shifts the modes because it introduces some potential, additional potential, but it shifts not all the modes, but modes that, for example, if we put a particle here, it should shift all modes that are existing at the point. So it shifts all these modes, but obviously not these modes. And by measuring the spectral changes, here we can easily derive the position of the particle on the surface. This is idea which also was proposed and somehow tested by Professor Sumetsky in capillary snap for optofluidic capillary microresonators. And the second promising application is a low repetition rate microcomb. The idea is to create microcomb, to create a device generating a number of equidistant lines owing to Kerr non-linearity, but with the special forms. In general, we should be able to shape the surface of the fiber in such a way that the azimuthal agent frequency series or azimuthal free spectral range difference in wavelength, difference in frequency for azimuthal modes can be exact multiple for free spectral range of axial modes. So we can like build up a microresonator with the series of modes which are close to each other and with a very large number of these modes because of different azimuthal numbers involved. In this case, it should be a low repetition rate because the distance, spectral distance between adjacent axial modes is quite small, and at the same time broadband because of large number of modes, microcomb device, and this is another promising application. Okay, I want to conclude here. So whispering gathering modes on the surface of an optical fiber form a multi-mode system which can be controlled by introducing effective radius variations, not only by heating of interlaser inscription, but also by mechanical stresses, by bending the fiber or by using some geometrical tricks, using the fiber cleave. And these microresonators, cylindrical microresonators, have some promising application that still should be checked. Okay, thank you very much for your attention. I'm done.
Thanks, Ilya. So, colleagues, we are open for questions. Let me probably start. So, Ilya, I'm wondering, so you have shown that parabolic potential allows you to somehow compensate the dispersion, the system. I'm wondering if you can obtain negative dispersion in such system in order to, I don't know, shorten the pulses or something like that. So, is it possible to do so?
I think yes, like in any type of quantum mechanical yeah, I think yes, that should be not okay. So am I right that you just need to get proper? Okay, I can't answer it right now. I should think about it. In my opinion, yes, you can.
So it seems that you, before you introduce this shape of the potential, you have kind of positive dispersion, and for this reason you have the so the elongation of pulses or something, as it is shown in your images. Yes, here at the left.
Yeah.
Yes, and so probably you compensate this somehow by means of potential. And I'm wondering, can you even introduce such a potential that would have negative a negative effect for that, and would even shorten the pulses you have. So maybe that's something so we should think about.
Yeah, of course, yes. I should say that it should be kind of obvious, but I'm sorry I cannot answer it now. Okay, probably that's an option.
Yeah. So another question is the following: how slow can be those waves? So you are talking about millimeters per nanosecond, as far as I got. So can you? So what is the limit? The real limitation for your for the speed, for the velocity of the mode, the minimal velocity of the mode you can obtain. So how efficient you can slow down light in the systems?
Well, it's actually, it depends on how steep slope you can introduce. I don't remember the exact numbers, but I believe the slope can be like
So, basically, I don't see any fundamental limit.
Yeah. From my opinion, no. It just limit of a methodic you use to introduce this slope. Of course, you cannot do it with bending because it's kind of smooth change of effective radius, but you can do it with CO2 laser, and certainly with femtosecond laser radiation, I think you can also slow it down like 10, probably 1,000 times more. I need to look at the particular maximum effective radius variations which you can introduce.
I see. But that would be so. From the practical point of view, I think it should be interesting. So to minimize the size and so on and so forth.
Mm-hmm.
Okay.
Yeah, thank you, Anton. You're
right. Guys, do we have any questions? Any more questions from the audience? Okay then. So Ilya, thanks a lot for joining us this nice summer Friday.
And thank you very much for listening to me.
And giving a brilliant talk at our seminar. So before we finish, I should know that we don't have any seminar next week, and the next seminar will be announced on our new seminar webpage. Please visit it, so you may subscribe and receive the email on that. I'll just give you the links to that. So with this, I would like to thank everyone for joining, and have a nice weekend. Thank you, Ilya.
Thank you very much. Thank you. Bye.